Hello students, in the first lecture we had defined what is how many kinds of mapping from one group to another group exist and from one group to the same group exist. Now in the second lecture and also in the second lecture we have discussed problem based on different type of homomorphism, and now in this lecture we'll discuss homomorphic groups. Then let's solve the problem based on homomorphic groups. Prove that the additive group of complex numbers a plus iota b, where a and b are integers, is isomorphic to the multiplicative group of rational numbers 2 is power a and into 3 is power b and a and b are integers. What is proven? Prove that the additive group of complex numbers a plus iota b, where a and b are integers, is isomorphic to the multiplicative group of rational numbers 2 is for a into 3 is for b, where a and b are integers. So the given solution is given. Let G be a G is the set of all a plus iota b complex numbers when a and b are integers. Be a additive group of complex numbers, and G dash is a group consisting of 2 by A into 3 by B, where A and B are integers. Be a multiplicative group of rational numbers. And let's define a mapping. Let's find mapping from G to G dash by f of A plus iota b is equal to 2 by A into 3 by B for all A plus iota b belongs to G when A and B are integers. Our aim is to show that G and G dash are isomorphic groups. In order to show that G and G dash are isomorphic groups, we have to show the mapping. What the mapping we have defined in this problem, we have to show that this mapping is homomorphism is 1 1 as well as 1 2. So in order to show this is isomorphic, these groups are isomorphic, we have to show these three things. So let us show one by one. To show F is homomorphism, let us take two elements, domain set x and y belongs to domain set belongs to G. Be any arbitrary elements. If they belongs to G, then they will be the type x is equal to a plus iota b, y is equal to c plus iota d, where a, b, c, d are integers. Then f of x plus iota will be equal to f of x plus y will become f of a plus iota b plus c plus iota d, f of a plus c, this part here will equal to a plus c plus iota b plus c. So now definition of mapping. This can be written as 2 is power a plus c, a plus c, 3 power a plus b. This can be written as 2 is power a, then rational number 2 is power a, 2 is power c, 3 is power a, 3 power b. Rational number addition is commutative, so this can also be written as, it can be commuted. So 2 is power a, 3 is power b, 2 is power c, 3 is power d. 2 is power a, 3 is power b, b is equal to f of a plus iota b. Definition of because C power D is equal to f of C plus D. So f of A plus B is equal to f of x plus y is equal to f of x into f of y. So implies f is a homomorphism. Now we will show that f is 1 1. Let us take two elements x and y belongs to G such that f of x is equal to f of y. Substitute the value mapping is equal to f of a plus iota b, x is type a plus iota b, y c plus d. So f of a plus iota b is equal to f of c plus d. F of a plus iota b is equal to a, c power b, f of c plus d, f of c power a, c power c, c power d. G is a group and cancellation of whole. So if you apply left cancellation by 2 for c minus c and the right cancellation by 2 3 for d, we got this 2 power a minus c and base is a power z. This is law of indices holds true in the group. 2 power a minus c, 3 power b minus c is equal to how much? Equal to 0. equal to 1, equal to 0. This implies two numbers are equal if their powers are equal. This power even c, this power even c is equal to plus 0, so c power 0 implies a minus c is equal to 0 and b minus c is equal to implies a plus c is equal to b. This implies a plus item is equal to c plus item implies x is equal to y implies f is then 1 1. Now I want to show f is onto, let us take y belongs to g dash be any element such that, and then there exists a and b belongs to I such that 2 is for a and 2 is for a, 3 is for b is equal to y. That is equal to, let's say that is equal to f of a plus item is equal to y. For each y belongs to g dash, there is this x is equal to a plus item b belongs to g such that for where a belongs to g such that it, where a belongs to g implies f is a homomorphism, f is 1 1, f is on 2 implies f is isomorphism of g to g dash and implies g and g dash are isomorphic groups. Second problem, prove that multiplicative group of all matrices A, B minus BA, where A and B are real numbers, not both zero, is isomorphic to the group of non-zero complex numbers A plus iota B, where A and B are real numbers, and A square B square not equal to zero, means both the A and B are not equal to zero under multiplication. Both prove that under both of set of matrices under multiplication, and this is set of complement under multiplication. So now given is G is the set of all 2 by 10 matrices such that A, B minus BA in the real numbers such that respect is not equal to 0. Be the multiplicative group of matrices. Economics. And G dash is the set of all complex A plus iota B where A, B are real numbers such that A square B square is not equal to both are not equal to 0. Be the multiplicative group of non-zero complex numbers. Now define a mapping f from G dash to G, complex number 2 matrices, such that f of A plus iota B is equal to A, B minus B, A. Second order matrix for all A plus iota belongs to G dash. Now I want to show that this the groups these two groups G and G dash are isomorphic. For that we have to show f is the homomorphism, f is 1 1, so f is 1. So that is so f is homomorphic. So let us take x1 belongs to G dash. X1 G dash be any two elements, then x will be type A plus iota B, y plus C plus iota D for some A, B, C belongs to R, such that A is equal to B is equal to 0, C is equal to B is equal to 0. So if you multiply x into y, you got A plus iota B into C plus iota D is equal to AC minus BD plus iota AD minus plus BC. So f of x is equal to f of this, f of A, AC minus BD minus plus iota AD plus BD. So you can convert it into by definition of the mapping. This is written as AB, AB minus BA. So this is the product of these matrices, AB minus BA, CD minus DA. This is equal to f of A plus iota B, f of iota B, and this is equal to f of C plus iota B. So f of this is equal to f of x into f of y. This is equal to f of x into f of y. So f of x y is equal to f of x into f of y implies f is a homomorphism. Now to show f is 1 1, let's take two elements x and y belongs to G dash such that f of x is equal to y. So f of x is equal to a plus iota b, y is equal to c plus iota d, f of a plus iota b equals 3. So now put the value mapping, you can do mapping here a b minus ba, b minus da. Two matrices are equal if the corresponding elements equal. A is equal to c, b is equal to d, b is equal to d. Matrices equal if A is equal to c, b is equal to d. So equal. Then now substitute the value a plus this implies if you could see b to d implies A plus iota B is equal to C plus iota D, implies X is equal. So F is the mapping F such that F of X is equal to F of Y implies X is equal to Y implies F is a one mapping. Now to show F is onto mapping, for we have to take the range set. For any A, B minus BA belongs to G, where A, B are real numbers, I will be equal to 0. Here exists A plus iota B belongs to G such that F of A plus iota B is equal to A, B minus BA 7 order implies F is 1. For second pair implies F is a F first is F is 1, second F is 1, second third implies F is 1 to imply G dash and G are isomorphic. Next one is prove that if for the group G, for a group G, F is mapping from G to G is given by Fx is equal to x cube. X is equal to x cube and x goes to G is an isomorphism, then G is everywhere. If this is isomorphism, then it should G is everywhere. So given is, so we know that F is a mapping G to G defined by F of x is equal to x cube for all x goes to G is an isomorphism. Isomorphism means it is a homomorphism, it is one, it is one. But we have to prove it G is an absolute. We have to show that x y is equal to yx for all x y belongs to G. For all x y belongs to G. So the step first, we will show that for all x belongs to G, we have to show, we have to remember this step. We have to show that x square also belongs to Z. We have to set of this equal center. Now show this, we have to take the, now show that G is commutative, we have to take that from the set. We'll show that for all x belongs to G, x belongs to G. So for that, let us take x, y belongs to G. We have x belongs to G. We have x cube, G, x belongs to G. G is a group and 2 is group. If x belongs to G, G belongs to G, x is x square also belongs to G, x cube also belongs to G. So x square belongs to G, x cube belongs to G, G and x belongs to G, and this belongs to G. So we have to take this element. This element. We have to remember this step. Now f of x cube x into minus 3g x cube is equal to how much? F by definition is equal to x minus 3g x cube whole cube. Now with this result, if a and g belong to a and small g belong to g, then a inverse g a is for n is equal to a inverse g for n a for all n belongs to I. So it's contained as using this here. So this is equal to x is equal to minus 3, g is equal to 3, x by 3. So now, again, definition of function. This contains f of x inverse, this is f of g, f of x. Because f is a homomorphism. Now, by definition of homomorphism and by definition of isomorphism, by definition of x is a isomorphism. So, by definition of function. Okay. Now, here, this is equal to this. We use the definition of homomorphism. F of x gx is equal to f this into this. Now we got, so f of x is minus 3 gx 3 is equal to f of x inverse gx. Implies, because this is the isomorphism, therefore this is 1 1. So f of this equal to this implies element side equal. Since they are equal implies, because they are the elements of G and G group. Therefore, left and right cancellation both holds true. So apply right cancel by x and left cancel by right cancellation by x inverse and right left cancel by x. We got x minus 2 G x is equal to G. X is equal to G. This implies again apply right cancellation by x once and twice again. So we got and this is left cancel by x. So we got x is x inverse g x square is equal to xg. Again apply that cancel by x. So we got g x square is equal to x square for all x. This implies x square belongs to ZG for all x1. X1. First part is over. Now, second part is you have to show that G is an abelian group. G is an abelian group. As F is mapping G to G is a homomorphism. So for all x belongs to G, f of x y is equal to f x equal f of y. So xy definition of for mapping f x y is equal to x y cube equal to x cube by cube. So this contains x y into x one x y cube. G is a group consider whole group. So you can write the left cancellation by x and right cancellation by y inverse x inverse and y inverse. After applying left cancellation by minus x inverse and right cancellation by y inverse, we got from this equation this is yx is equal to x square y square. As x belongs to g, so x square g is a group, so x square also belongs to g, and y also belongs to g, y square also belongs to g, and x square belongs to central group g, and y belongs to g, y square also belongs to central group. So the x square is element of g, therefore x square y square is equal to y square x square. So choose the value for x square y square from here. X square y square is equal to y square x square. So yx is equal to y square x square. Now again applying left cancellation by y inverse and right cancellation by x inverse, we got xy is equal to yx. For all xy belongs to G, imply G is an abelian group. Thank you very much.